So we're going to start with some of our calculations today. It's looking at something called gram formula mass. A quick review, remember a mole is 6.02 times 10 to the 23 particles. These could be atoms or molecules. It's based on carbon-12, and it allows us to relate AMUs directly with grams. And this is the chemist's fundamental unit, and we abbreviate it MOL. As we did our little chair, if we haven't done this, sorry, I'm not sure when exactly we're going to do this. We have a little chant that reminds us that the table tells us the grams in 1 mole. So whenever you look at a number of grams that are given on the periodic table or that atomic mass on there, what you're actually looking at is how many grams you would have if you had 6.02 times 10 to the 23rd particles. So again, this is based on carbon-12. We use something called the gram formula mass. So formula mass is the mass of 1 mole of a substance. This is technically an AMUs. Sometimes it's referred to as molecular mass. We will be using what's termed the gram formula mass. I use the abbreviation GFM quite frequently. Gram formula mass is the mass of 1 mole of a substance in grams. So it's in the unit of actually grams per mole. So since the table tells us the grams in 1 mole, we're going to actually use the periodic table to determine how many grams we have in each mole of a substance. I just like this confused girl's face. So GFM is a frequently used abbreviation meaning gram formula mass, and it's what we're about to do right now. Little note on sig figs here. This is generally considered adding or subtracting, so our sig figs are limited to the number that we plug in with the least number of decimal places. Generally, I don't like to round GFMs till the end of a problem. You'll kind of get the hang of what I mean by this. So we're going to start with the compound C4H10. So the very first thing we do is we go to the periodic table and we find the mass of each of these individual elements. We are actually going to keep the decimals with these. In more Regents level problems, we do not need to do that. But when we want to, make sure that we have the proper number of significant figures, we will actually do that. So you look at the mass of each of these elements on the periodic table. We need to determine how many atoms of each one we have. So we have 4 carbons and we have 10 hydrogens. And then we actually do multiplication here, but it's really as a substitute for addition. It's just a shortcut. So the reason I'm mentioning it is it doesn't change our sig fig rules. We're still based on our number of decimal places. So since we have 4 carbons, we'll multiply that by 12.011. And we have 10 hydrogens, which we will multiply by 1.00794. So you're going to punch those into your calculator. Oops, I lost my little answer bar there. And that should give us 58.1234 grams per mole. In terms of my significant figures, because I have 3 decimal places here, I kept 3 decimal places here. Many of the problems that we're doing, if you keep the gram formula mass, if you keep the gram formula mass with all your decimal places, it doesn't create a huge issue, so a lot of times it's okay to do that. So calcium nitrate has the formula CaNO3(2). We're going to find the mass of each element on the periodic table. So 40.08. Nitrogen is 14.0067. And oxygen is 15.9994. In our formula, we have 1 atom of calcium. We have 2 atoms of nitrogen. And we have 6 atoms of oxygen. So please be comfortable. Make sure you're comfortable with where I'm getting this. Remember, this 2 means there's 2 groups of these. You can also visually count them here. These are our nitrogens. There's 2 of them, 6 blue oxygens. So we're going to go ahead and we are going to do 1 times 40.08. So I'm just writing 40.08. We have 2 nitrogens times 14.067. And we have 6 oxygens times 15.9994. You're going to punch these in your calculator. Remember, this still technically counts as adding. So with proper sig figs, we get 164.09 in the unit of gram per mole. Now, hydrate's a little bit strange. We do deal with these from time to time. You've actually looked at this in lab before. This was that blue stuff that you heated up, it lost its color. You add water to it and it gains its color back again. So what actually happened when you did that lab, this compound is a salt, copper sulfate, that is associated with water. When you heat it, you evaporate the water off of it. But when we initially have that compound in existence, it has these waters kind of physically associated to it. So it's not an actual chemical bond, it's kind of a weird situation, but we can physically separate them by heating. When we look at calculating the gram for, okay, let me get control of this. When we look at calculating the gram formula mass, what's a little bit weird is this dot tends to indicate to students that you are multiplying by that water, and actually you're not. So we're just going to add all of these atoms together when we calculate our gram formula mass. So I'm going to go ahead and find copper on the periodic table. So copper is 58.93, oops, sorry, going to the wrong element. 63.546. I only have one of those, so I'm actually going to do step 1 and step 2 together, show you how to do that. I only have one sulfur, so my sulfur atom is 32.065. I have a lot of oxygens. I have them in 2 places. I have 4 right here, and because there's this 5 here, it actually means I have 5 over here. You can handle this a couple of different ways. You can actually do each part on its own. I'm just going to combine them together. So I have 4 oxygens in the first part of the compound and 5 in the second, which gives me 9 oxygens times 15.9994. And last but not least, I have 5 groups of water, which means I have these 10 hydrogens right here. So I'm doing 10 times 1.00794. And just to give you a little idea of kind of how the formula relates to that, if you were to count things on here, copper is straightforward, sulfur is straightforward. The blues are oxygens. 1, 2, 3, 4, 5, 6, 7, 8, 9 oxygens for your hydrogen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's where those numbers come from. Now we're going to add all those together. So you can take a minute, punch them into your calculator. Pause the video if you need to. It's a lot. And what you will get is 249.685. So we're able to keep 3 decimal places there. We're limited by copper and also sulfur. Please pause the video for a minute, and I will put work up for each of these, including the answers. So I've shown the work for each of these. The first one was 119.002. Second one was 10.09. The 3 is 52.0763. And the last one was 262.585. Now, we can also do conversions between grams and moles based on these conversion factors that we have, meaning we know now the relationship, between how many grams we have in each mole. So that actually becomes a conversion factor for us. So we can easily tell by looking at the periodic table. If you put your finger on magnesium, every time we have a mole of magnesium, it's going to weigh 24.305 grams of magnesium, 24.305 grams. If you knew you had 2 moles, you'd very easily just double that. So that makes a ton of sense. That's pretty easy math. But a lot of problems aren't going to be quite that simple. So we're going to talk about using dimensional analysis to solve these, which for these, they're fairly straightforward, but as we get into more complicated problems, dimensional analysis will be very helpful. So we're going to determine how many grams are in 3.66 moles of NaCl. So the first thing that you need to do is determine sodium chloride's gram formula mass. So I'm going to give you that right now. If you want to backtrack and check, you can pause the video for a minute, make sure you know how to do that. This can be written either as 58.44277 grams for 1 mole, or as 1 mole is equal to 58.44277 grams, depending on what we need in the problem. Now our starting amount that they're giving us is 3.66 moles. And we need to have our answer come out in grams. So we need to cancel out moles and turn it into grams. So as I'm looking at my two conversion factors, I'm going to want to have moles on the bottom. So I'm going to choose this guy. So I'm going to write 58.44277 grams is equal to 1 mole. And I'm just keeping all the digits there, even though they're not truly all sig figs, and then I'll round at the end. So I can go ahead, my moles will cancel out. You're going to multiply 3.66 times 58.44277, which should give you 214 grams. And at that point, I did look at my sig figs. This number has 3 sig figs, so that's what I'm limited to. And you should really ask yourself if this makes sense. So I said, okay, 58 grams is 1 mole, and I have, about 3.5 times that. So that does make sense that that would be over 200 grams. The other thing that I can do is I can turn grams into moles. So by looking at carbon on the periodic table, if I have 12 grams, and again, I kind of took the decimal out to simplify this, but I know that's about a mole. If I had 24 grams, I can say pretty safely that's about 2 moles. So if I want to find out how many moles are in 92.2 grams of iron oxide, I'm going to start with my gram formula mass. And again, if you'd like to check that, you can pause the video and double check it. This can be written either as 159.6882 grams over 1 mole, or 1 mole over 159.6882 grams. So I have to think about what I want to get rid of. So my starting amount that they're giving me in the problem is 92.2 grams. And I need to turn this into, ultimately, moles, which means I need grams to cancel. I need grams on the bottom. So this time I'm going to pick this one. So essentially this means I'm dividing. And again, a lot of you are probably thinking, hey, I just know I need to divide. I'm just going to do that. With these simple problems, that's totally fine. What's nice about this problem-solving technique is we're going to get into much harder problems, and being able to use dimensional analysis will be very helpful. So that allows my grams to go away. So you're going to punch into your calculator 92.2 divided by 159. And that gives you 0.577 moles. My sig figs here are 3 based on 92.2. Now if I want to think to myself if this makes sense. So 1 mole is about 160, and I have 92.2 grams. So, that should be a little bit more than half. So I've got a couple of problems up here. I'm going to pause the video for a minute, fill in the work. You can pause the video as well and try them out, and then check your answers. You can go ahead and check your answer on each of these. I filled in the work as well. On the first two, you're dividing. What's nice about dimensional analysis is it does remind you what number goes on top. The small numbers there are your gram formula masses that match right what's in the calculation. So do double check that you're proficient at calculating those as well. And this wraps up the basis of mole calculations. We've got a lot more to go. We'll practice this a little bit in class tomorrow.